Black holes are among the most mysterious and fascinating objects in the universe, natural laboratories for studying gravity and time. They are not merely regions where matter is highly concentrated, but points where the laws of physics reach their limits and gravitational effects become extraordinary. At the center of a black hole, gravitational pull becomes so intense that nothing can escape, not even light, giving them an almost mythical power. Yet what makes them truly captivating is the way they influence time, dramatically slowing it down as one approaches them. This slowing is not merely a theoretical concept, it is a demonstrable reality explained by Einstein's general theory of relativity, which shows that time is not uniform but can be shaped by gravity. Around a black hole, time gradually slows as the gravitational field intensifies. For a distant observer, any event occurring near the event horizon appears to unfold slowly, every motion of matter and pulse of light extended, as if the universe were paused in that region. This creates a striking contrast between the local experience of objects falling into the black hole, which continue to perceive time normally, and the perspective of someone observing from afar, for whom time seems to stretch into eternity. This radical difference in perception shows that time is not a universal constant but a flexible dimension. Shaped by gravity and the mass of surrounding objects, the effects of black holes on time are accompanied by a series of spectacular physical phenomena. Matter approaching their center is stretched and deformed in extreme ways, a process often called spaghettification, where objects are warped by differential gravitational forces. The light emitted by these objects becomes increasingly redshifted and faint as it nears the event horizon, and its trajectory is bent by the gravitational field. Astronomers can detect these effects by observing stars and gas near black holes, using telescopes and other instruments to measure motion, velocity, and spectral changes in light. In this way, black holes become true windows into the extreme nature of time and space. Studying black holes and their effects on time provides profound insights into the universe and how it operates on the most extreme scales. They reveal that time does not flow uniformly, that gravity can compress and stretch events, and that reality as we perceive it on Earth is only part of a far more complex whole. Black holes challenge our understanding of fundamental concepts like causality, simultaneity, and the perception of events, showing that the universe is far more flexible, dynamic, and strange than we might imagine. Every second that passes near a black hole, time merges with gravity, and matter and energy are caught in a cosmic dance that defies ordinary intuition. By studying them, we learn that the universe is not merely an empty and peaceful space but a realm of incredible forces, where even time itself can be shaped and transformed by the presence of the most extreme cosmic objects. As one moves closer to a black hole, the effects of its extreme gravity on time and space become increasingly dramatic. The process known as time dilation intensifies, meaning that time for objects near the black hole slows relative to a distant observer. Matter, light, and even electromagnetic signals are stretched and delayed, creating the impression that events unfold much more slowly than they would elsewhere in the universe. For an observer far from the black hole, a star or spacecraft approaching the event horizon seems to take an eternity to arrive, its movements slowed and elongated in a way that appears almost frozen in time. Yet locally, for the object itself, time passes normally, highlighting the stark relativity of temporal experience under extreme gravitational conditions. This extreme environment also produces profound distortions in space. Gravitational forces near the event horizon stretch and twist space, curving the paths of nearby objects and even bending the trajectory of light. This spatial warping, combined with time dilation, creates a region where the familiar rules of motion and causality are pushed to their limits. Phenomena like gravitational redshift, in which light emitted from near the black hole shifts toward longer wavelengths, provide observable evidence of these effects. Astronomers study these signals to map the motion and behavior of matter around black holes, allowing them to reconstruct the dynamics of regions where time itself is dramatically altered. For physicists, black holes are invaluable natural laboratories. They allow the testing of fundamental theories, such as general relativity, under conditions that cannot be reproduced on Earth. Observations of stars orbiting supermassive black holes, gas streams spiraling inward, and the energy emitted from accretion disks all confirm that time slows significantly in strong gravitational fields. This understanding deepens our knowledge of how the universe operates, from the formation and evolution of galaxies to the behavior of matter under extreme pressures and densities. For the wider observer, black holes are both awe-inspiring and humbling. They demonstrate that time is not a fixed, universal constant but a dynamic dimension that can be stretched, compressed, and shaped by gravity. By studying the interplay of time, space, and matter near black holes, we gain a glimpse into the profound complexity of the cosmos, learning that the universe is far more fluid, strange, and wondrous than our everyday experience would suggest. The effects of black holes on time and space extend far beyond theoretical predictions. They can be observed and measured, providing concrete evidence of the extreme nature of gravity. Stars orbiting near supermassive black holes, for example, exhibit motions that reveal the intense warping of spacetime. Their velocities, trajectories, and the shifts in the light they emit all carry information about how gravity stretches and compresses time. Even light emitted from matter approaching the event horizon becomes increasingly redshifted, its wavelength stretched as the flow of time slows, creating a cosmic signal that astronomers can detect across vast distances. These observations allow scientists to quantify the degree of time dilation and confirm the predictions made by Einstein's theory of general relativity. In addition to individual stars, larger structures like accretion disks around black holes demonstrate the dramatic influence of extreme gravity. Gas spiraling inward heats up and emits X-rays, which can be measured to study both the speed of rotation and the effects of time dilation on the emitted radiation. Events that occur near the event horizon, such as flares or the collision of matter within the disk, appear prolonged to distant observers, stretching over hours or even days, while locally they may unfold in mere minutes. Such observations provide a rare window into environments where the normal flow of time is drastically altered, revealing the interplay between gravity, motion, and the passage of time in a tangible way. Gravitational waves produced by merging black holes also carry signatures of time distortion. As two black holes spiral toward each other, the warping of spacetime affects the timing and frequency of the waves they generate. Detecting these signals with instruments like LIGO and Virgo allows scientists to study the dynamics of black hole interactions, including how time behaves under the most extreme gravitational conditions imaginable. Each observation reinforces the reality that near a black hole, time does not flow uniformly, and the universe operates under rules that challenge everyday intuition. These measurable effects not only confirm theoretical predictions but also expand our understanding of the universe. By studying how time slows near black holes, physicists gain insight into the fundamental nature of reality, learning how gravity shapes the fabric of spacetime itself. Black holes thus serve as natural laboratories, teaching us that time is not fixed but flexible, and that the universe contains regions where the ordinary flow of events is profoundly transformed. Through these observations, we come to realize that the cosmos is far more dynamic, strange, and wondrous than our daily experiences on Earth might suggest. Looking toward the future, the study of black holes and their effects on time offers profound insights into the workings of the universe. The dramatic slowing of time near a black hole reveals that time is not a uniform, universal constant, but a flexible dimension influenced by gravity. This understanding has implications beyond theoretical physics, affecting how we might navigate space, study the early universe, or explore regions near extreme gravitational fields. Black holes are not merely destructive objects, they are dynamic agents that shape the evolution of galaxies, influence star formation, and affect the trajectories of nearby matter. The extreme time dilation near black holes also challenges our basic concepts of causality and simultaneity. Events that unfold near the event horizon appear to stretch into eternity for distant observers, demonstrating that temporal experience is relative and dependent on gravitational context. This compels scientists to rethink how events are connected across space and time, highlighting the extraordinary flexibility of the cosmos. Black holes show that time itself can be manipulated, slowed, and shaped by the forces of gravity, revealing a universe that is far more intricate and dynamic than our everyday perceptions suggest. For those observing from afar, black holes evoke both awe and curiosity. They are not simply cosmic vacuum cleaners consuming matter and energy, they are architects of spacetime, capable of bending the very fabric of reality. Studying them allows us to understand the limits of physical laws and the extreme conditions under which time and space behave in unexpected ways. Every observation deepens our appreciation of the universe's complexity, showing that it is not static or uniform, but a dynamic arena of forces and phenomena that continuously transform matter, energy, and even time itself. In the end, black holes teach us that the universe operates on scales and under conditions that defy common intuition. Time near these objects is malleable, space is distorted, and reality becomes a fluid interplay of forces beyond ordinary experience. By exploring these cosmic phenomena, we gain not only scientific knowledge but also a deeper sense of wonder, discovering that the universe is a vast, dynamic, and astonishingly strange place, where the rules we take for granted on Earth are only a small part of a far greater cosmic story.